Rocket engines propel by pushing mass oppositely. This fundamental principle, akin to a powerful hose propelling against a user's arm, is crucial. However, early designs using high-pressure gas tanks and releasing them, like a Mentos Cola rocket, proved less efficient. These less sophisticated methods lack the controlled thrust and precise energy management needed for complex space missions. Efficiency demands a more controlled, focused method of expulsion. Traditional approaches are insufficient for complex space travel demands. A new method is needed for better use of expelled energy. SpaceX's innovation lies in the engineering that drives controlled explosion, leading to a more efficient propulsion system. Boosting rocket efficiency hinges on controlled explosions. Explosive expansion generates high pressure, which, when confined, forces propulsion. This eliminates the need for bulky, high-pressure gas tanks, replacing them with direct use of combustible materials. However, controlling the resulting explosion is the key challenge. Uncontrolled explosions are inefficient and unpredictable. SpaceX's approach, though, focuses on leveraging this powerful directed energy source. The challenge lies in harnessing this explosive power precisely and safely, allowing for the smooth delivery of immense thrust, a critical component of advanced rocketry. Finding a manageable way to control explosions is essential. Pumping fuel and oxidizer into an active explosion demands immense pressure, a challenge addressed by SpaceX's innovative turbopumps. The Raptor engine's high combustion chamber pressure, 300 bar, necessitates a powerful yet lightweight solution. Conventional pumps prove inadequate and excessively heavy, hindering the engine's overall performance. Turbopumps, instead, use a controlled explosion to drive a turbine, efficiently pumping propellants at high pressure. This ingenious approach converts a portion of the engine's energy into mechanical work, overcoming the weight limitations inherent in traditional pump designs. This sophisticated approach is crucial for the engine's performance and structural integrity. Optimal fuel and oxidizer ratios for turbopumps generate intense heat, posing a significant threat of melting engine components. SpaceX engineers address this by designing turbopumps with intentionally lower efficiency. This design choice allows for the injection of excess fuel or oxidizer into the combustion chamber, effectively cooling the engine. However, this cooling mechanism necessitates discarding some propellant, a trade-off inherent in rocket propulsion. This intentional inefficiency ensures the engine's structural integrity by preventing overheating, although some propellant is inevitably wasted. The design compromises some efficiency for crucial temperature control in the critical turbopump components. Rocket engines fall into two broad categories: open-cycle and closed-cycle. Open-cycle engines, exemplified by SpaceX's Merlin engine, prioritize simplicity but suffer from lower efficiency due to propellant waste. Closed-cycle engines like Raptor are designed for optimal efficiency by minimizing propellant loss. The Raptor engine's closed-cycle design is a crucial aspect of its superior performance. This design choice eliminates the propellant waste inherent in open-cycle systems, maximizing the thrust-to-weight ratio and efficiency. The fundamental difference between these two approaches lies in their respective strategies for propellant utilization and management. This design choice directly impacts the overall performance and operational characteristics of the rocket engine. SpaceX's Raptor engine stands out with its innovative closed-cycle design. This design prevents propellant loss, a key factor in its exceptional performance. The fully closed-cycle system ensures every drop of fuel and oxidizer contributes to thrust, unlike open-cycle engines that waste some propellant. This design choice represents a significant advancement in rocket technology. Raptor's ability to utilize all available propellant effectively sets it apart from existing designs. This revolutionary design is a significant step forward in the field of rocket propulsion, leading to higher efficiency and thrust-to-weight ratios. This feature is crucial for the engine's superior performance characteristics. Developing the Raptor engine presented a significant challenge, controlling the extreme temperatures generated by high-pressure operation. High pressures necessitate high temperatures, especially within the preburners. SpaceX addressed this by developing specialized materials like SX500 and other advanced alloys. These materials are critical for withstanding the extreme operating conditions within the engine. The intense heat and pressure in the preburners demand robust materials capable of withstanding extreme thermal and mechanical stresses. These materials are crucial for the engine's longevity and performance. This specialized material development is essential for maintaining the Raptor's structural integrity. Cooling engine components is vital for Raptor's operation. SpaceX employs a sophisticated cooling system, circulating cryogenic liquid oxygen and methane through channels surrounding critical components. This method cools the metal while heating the propellants, ensuring structural integrity. Further, film cooling techniques are applied to engine surfaces, creating a protective layer of cooler propellant. These methods are crucial for preventing overheating and maintaining the engine's structural integrity under extreme operating conditions. Maintaining optimal temperatures is essential for the engine's sustained performance and prevents critical components from being damaged by excessive heat. This active cooling system is integral to the Raptor's successful operation. Choosing methane as Raptor's fuel offers a balance of efficiency and practicality. Methane's properties provide a more efficient combustion process compared to RP1, while remaining easier to handle than liquid hydrogen. This balance is critical for reusable rocket designs, reducing complexity and enhancing the potential for reuse. This makes methane a practical choice for future space missions, where reusability is paramount. Methane's clean exhaust further contributes to the potential for reusability, reducing the accumulation of harmful byproducts. These factors combine to make methane a highly suitable fuel for a reusable space vehicle like Starship. The Raptor engine's design anticipates future upgrades and iterations. This iterative development is a key characteristic of the engine, distinguishing it from other rocket designs. Raptor's design from the outset allowed for significant performance improvements between versions, like Raptor 2 and 3, which saw substantial increases in thrust and decreases in weight. This iterative approach allows for continuous optimization and adaptation. These advancements underscore SpaceX's commitment to continuous improvement in rocket engine technology. This adaptable design philosophy is essential for meeting evolving technological and performance demands. Such iterative improvements are key to the engine's ongoing evolution and future potential. SpaceX's Raptor engine, while highly advanced, still falls short of its initial performance goals. Despite significant improvements between versions, the engine's performance is still slightly below target, particularly concerning specific impulse and thrust. Fundamental physical limitations may be hindering further efficiency gains. Further development will likely be necessary to fully realize the initial design goals. This suggests that further breakthroughs in material science or engine design may be necessary to reach the previously stated performance objectives. SpaceX's commitment to relentless innovation and iteration hints at continued development efforts to address these remaining challenges. The final performance may be limited by the fundamental laws of physics. SpaceX's Raptor 3 engine, improvements, but not perfection, says Musk's SpaceX CEO Elon Musk announced Wednesday that the Raptor engine, a crucial component of the Starship launch vehicle, is not yet perfect and requires further refinements. Musk, in a social media post, stated, "Still a few final touches to perfect Raptor." The revamped Raptor 3, unveiled in August, boasts significant improvements over its predecessor, Raptor 2. Musk highlights reduced weight, increased thrust, and enhanced efficiency, achieved through a fully regenerative cooling system, eliminating the need for a heat shield. He lauded the engine as a work of art, noting the substantial effort from SpaceX engineers. However, Musk cautioned that thousands of improvements are still needed, emphasizing the engine's induced mass can be further reduced. This iterative development is crucial for the engine's future performance. The Raptor engine powers SpaceX's ambitious Starship program, designed for lunar and Martian missions. The spacecraft is currently undergoing testing, with 6 previous flights completed. Next week's 7th test flight will carry 10 Starlink satellite simulators as payload, showcasing Starship's potential for satellite launches. SpaceX aims to recover the booster at the launch pad using Starbase's launch tower, reminiscent of its successful 5th test flight in October. However, safety remains paramount. In the event of any safety concerns, the booster will be safely splashed down in the Gulf of Mexico. The spacecraft is scheduled to be splashed down in the Indian Ocean during the upcoming test.